Good morning. Thank you for joining our final webinar in our three-part eBPF fall webinar series. eBPF, in particular with its driver-level hook XCP, has increased in importance over the past few years. As a result, the ability to rapidly debug and diagnose problems is becoming more relevant. This webinar, eBPF tooling and debugging infrastructure, will cover common issues faced and techniques to diagnose these problems. Copies of the presentation, archived replays of the webinars in this series, as well as any project code, can all be found on our eBPF page in the Technologies section of Netronome.com. Quentin Monet is a senior software engineer at Netronome, where he works on advanced technologies at the driver level, such as the software pieces of eBPF offload. He also contributes to several open source projects. Today, Quentin will elaborate on the use of bpftool for map and program introspection, the disassembling of programs to inspect generated eBPF instructions, and other methods such as using debug prints and how to apply these techniques when eBPF programs are offloaded to the hardware. At the conclusion of this webinar, we will have a QA session. Please feel free to post questions in the QA section of Zoom. Netronome recently launched a new support site that contains a knowledge base, forums, feature requests, and solutions. Please visit help.netronome.com for more information. Lastly, we'll have a drawing for an Amazon gift card at the conclusion of this webinar. Thank you. Now over to Quentin.
So I've been working on the eBPF parts for offload in the kernel, in the driver in particular, over the last year, and on the eBPF ecosystem in general over the last 3 years or so now. So that's why I'm making this presentation today. So just before we start with tooling and debugging, I'd like to present some short reminders about the eBPF infrastructure. So you don't usually program with eBPF by manually typing all your eBPF instructions. Instead, what you would do is compiling from a higher level language such as C or possibly Go or Rust or Lua into eBPF bytecode. That would provide you with an object file containing eBPF bytecode that you can later inject into the Linux kernel with the use of the BPF system call. Once this program is injected into the kernel, we want to make sure that nobody bad or wrong or unsafe or unsecure happens with the program. So there is a verifier in the Linux kernel which is responsible for checking that everything goes fine with that program. And once this program has been validated, we may or may not want to JIT compiles the program. That would be just-in-time compile. So that would provide better performance if we do translate the program to native instructions for the host. And at last, once they are loaded, the programs can be attached to one of the different hooks that we have in the kernel. So you have hooks for attaching program on TC traffic control, on the XDP interface at the driver level. You have other hooks as well that can be used for tracing and monitoring the internals of the Linux kernel, but this presentation only focuses on programs attached to networking hooks. So this diagram is exactly the same thing as what I just explained. So we have, for example, a C program that we can turn into eBPF bytecode with LLVM. We would later inject that eBPF bytecode into the kernel with the BPF system call. The kernel actually would verify the program on receiving it, and it can compile it for the host, or it could directly interpret it on the host, or it can also, for example, send the program to some hardware that supports BPF offload after compiling it for that hardware. So that would be the case for Netronome IGDO SmartNICs, for instance. So What we are going to do today is, well, as much as I would like, I won't be able to give you all keys for troubleshooting every issue with BPF program. Just one webinar is much too short for that. But what I want to do is to help you understand the basic tools available for working with eBPF, also for debugging eBPF programs at different stages of the loading process. So how we can see what eBPF instructions are running on the system. There are a number of commonly made mistakes that can be avoided if we are aware of those. So I would like to introduce a couple of them during the presentation so that maybe you can avoid them. And at the end of the presentation, I will provide some additional links and resources in order to help you find more information, more documentation, maybe about how to troubleshoot any issue that you would meet during eBPF development. So let's start with the very beginning. We want to compile some C program to eBPF bytecode. So the first tool that we would use is obviously Clang, which comes with LLVM, which is used to actually compile our program from C code. So I would use that command, for example. I would use Clang to emit LLVM instructions from my C program and pipe it into LLC, which is a tool coming with LLVM also, and tell him to produce BPF. I have a number of options here that are usually useful for compiling it to BPF bytecode. And at the end, I want to produce some ELF object file that will contain my BPF bytecode in one of its ELF sections. At this stage already, I am able to dump the instruction that were produced with by Clang from my C program. So I could use objdump or readelf to dump the contents of the file, but we have LLVM objdump, which is much more useful because the output that it gives is readable for people doing BPF stuff. So for example, this is my .o file, my object file that I tried to dump. And I see here that I had two eBPF instructions in that file. First one is move 0 into register 0. And the second one is exit. So 9.5 here at the left on the instruction would be the operation code for exit in BPF. B7 in hexadecimal, of course, would be move an immediate value into register. Register 0 would be the second 0 we have on the line. I think that's for the destination register. And the last 4 bytes stand for the immediate value that are moved. So this is a simple example on how you can dump instructions produced by compiling a C program. We could have provided the -G option to Clang that would have stored the original C code into the object file, and we would have been able to dump that as well with LLVM objdump -S, big S, in order to be able to map the C and the eBPF instruction produced. Some common mistakes, well, they are not so much at this stage because really everything regarding functional errors that we could get while compiling would be detected only later when we try to load the program. So you could have compiling errors. I mean, if you forget some semicolon in your C program, Clang will complain, of course. But mostly, maybe two things that we could note at that point would be don't use loops without unrolling them, because at the moment they're not supported by eBPF infrastructure. So you would have to use a directive like this one to tell Clang to unroll the loops when compiling the program. And also don't forget to inline functions if you are working on a kernel older than 4.16, because BPF function calls were only added at the time. But it tends to be less and less important since now we have function calls. Another way to compile your program would be to do that in 2 steps. So first step would be to compile from C to assembly. That's what I'm doing with that first command line. I'm trying to compile with -s from client, so that's to assembly, and my output file is sample read 0.s that I can done just after compiling, and I see that in the description of my function here, I have or0 equals 0 and exit, which are the two instructions that I had was compiled. And then I could change that code. I could edit this assembly file and, for example, replace or0 equals 0 to equals 1 here. And I could compile that again from the assembly file directly, not from the C file, into some object file here that will produce the same thing as when I did that in one step, except that if I have a more complex program than this simple example, I could edit my code directly, directly edit the assembly code, and then compile into something that would be understandable from the kernel. So now I have my eBPF bytecode. I want to actually use it, so I want to inject that into the kernel. I can use the BPF system code in a program that I write, but usually for networking programs, I already have a couple of programs that are able to inject BPF bytecode. That would be, for instance, the TC program from package iproot2. So traditionally, when you want to use a program on the TC interface, you start with creating a QDisk. For example, a CLS-ACT QDisk, which is a specific QDisk for eBPF programs. And then I attach my BPF program to that QDisk as a filter. So, I'm sorry. Here I say create a filter and add it on the ingress interface where the CLS-ACT has been created, and load the program in that object file here in the default help section, which is .text by default. This is the section of the object file where the program is stored. And direct action is take the written codes from that program as actions. I'll come back on that later. And so the program is loaded into the kernel, and then I can check with TC filter show that I have a program here, a BPF program, which is attached to my QDisk, and that it comes from the file with that name here, sample read 0.o again. The same thing is also valid for attaching XDP programs, loading and attaching programs. So I could use iplink set deb, the name of my network interface here, XDP, and load the program from this object file and from that section in the object file. And then I can also dump with iplink and see that I have a program, an XDP program attached to my interface. A couple of mistakes that we could avoid at this time include passing the correct section name on the command line. So by default, if you do not provide a section in your source file, can store that in the .text section. And if you do provide another name, don't forget to pass it to the command line. Otherwise, before even trying to load the program, TC or IP don't know where to find the eBPF bytecode in the file. So I spoke about the direct action option, which is recommended because this is most often what you want to do. So this option tells TC to consider return values as actions, for example, to directly pass or drop packets from your BPF programs instead of just taking the return value from the program as an ID for the queue to which you would like to push the program. That would be a different usage. And in particular, this option is mandatory for offloading programs with TC. You can have some other mistakes, some other error messages, sorry, such as device or resource fuzzy, typically with iplink, that would come from the interface already being running a program, an eBPF program. So you would like to use the -force option to overwrite it. Also, make sure your version of IP-root2 is recent enough to support everything you want to use in your program. If in doubt, try to get the latest version and to compile it. We provide instructions to download and compile IP-root2 in our Getting Started guide if you want. I'll provide a link for that at the end of the presentation. For example, if you want to use perf map events on an offloaded program, we recommend to use the version of IP-root2 coming with the kernel 4.18. So just make sure that you have something that's recent enough. And then once you have pushed your program to the BPF system call and to the system, to the Linux kernel, the kernel starts by applying a lot of verifications on your programs. So it performs checks both on the structure of the program and the control flow graph of the program, and also on individual instructions. So there are many things that could make the verifier reject your program actually. So for example, if I use an erroneous syntax for an instruction, that I use something that is not known, or that I don't use the instruction correctly, say I use a destination register for an instruction that does not take any destination register, then the verifier will reject the program. If I use more instructions or maps or branches that the kernel can support, then same thing, program is rejected. If I have loops at this time, also this might change in the future. If I have unreachable instructions, dead code, if I jump out of the program with jump instructions, if I try to access to some memory that's not in the data I can process with my program, these are as many reasons why the verifier could reject your program. So we have a list here. I'm not gonna read the list in details. Just if we have programs trying to use some BPF helpers, not GPL, of course that won't make it if you don't initialize R0, which is for the return value before exiting the program. Of course, you can have accesses to non-initialized memory. So a lot of things to be aware of, and you especially have to think quite low level when you're trying to debug some output from the verifier, because this is not even about things that are happening with your, say you are processing a packet, you want to process a packet. If you get an error message, it's not about what happens when you will be processing packets, it's what could happen, even if it will never happen. So the verifier is trying to make sure that no theoretical dangerous situation could happen. So we'll see a couple of examples, because there are two errors in particular that I would like to show you, just as some examples of the verifier rejecting programs. So I am using here a sample application that was published some time ago by Netronome. So there is a GitHub account that's Netronome BPF samples, and I'm using the L4 load balancer. So that's a layer 4 load balancer. We won't be focusing on how this demonstration works now, and even on if it works at all. I just want to have some base code in order to check what can happen with loading the program and the verifier. So I have modified this this application to introduce bugs. So let's see and just try to compile my my application. So I have a warning here coming from what I changed. Let's ignore that and try to load the program L4LB xdp.o. So I'm trying to load that to my interface NFP-P1 as an XDP program from the L4LB XDP.O object file. And it so happens that the program is in section called XDP. So what I get here is the output from the kernel verifier. It's sent straight to the console, and I can see that it provides a verifier analysis with instructions. These are BPF instructions. Those are actually the first BPF instructions processed by the program in that case, because it starts at 0. And what the verifier says is that we have an invalid access to a packet at offload 13 of size 1, and that it's in first register or 1 that it happens. So we have additional information here, or 1 offset is outside of the packet. So that's something that quite frequently when we don't, when we are not used to programming with BPF. So now let's see the code of that function. That's not here. BPF samples F4D. So this is the main function of my program. So I have more code on the top of the file here, all of this. And what I'm interested in is, at the moment, what I do with the first instructions of my program. So basically here, I'm trying to read the Ethernet prototype field of my packet. But before I do that, there is something that is missing here. That's really important. That's about checking that the program is actually long enough so that I can read this feed from the program header. So what I just did here, what is missing is a check on the length of the program. I must make sure that data plus the size plus the offset of the value I will try to read is not longer than the end of the packet. Otherwise, I must avoid doing the read operation. So if I add this check to the program, I won't have the same error again. I'll have another one instead. But so I'm trying again to load my program, and I don't have the error about accessing the packet. So again, what's important here is not that packets will create errors without this check, because all packets I get are at least 14 bytes long, because all packets have an Ethernet header, obviously. But the kernel must make sure that even if I was to receive something shorter than this, I would take every precaution that's needed to not crash my kernel. So I have to get this check. And now, so I have compiled my program again and tried again to inject that, but I get another error message, which is all7 invalid memory access, map value or null. This is also something frequent when you start with BPF programming. That would be because I'm using maps in my program. So if I do a research in my code on lookup, for instance, here I have map lookup lm. So this is a BPF helper, so a function in the kernel code by my BPF program. And it's used to perform a lookup in a hash table. Servers is a hash table defined above in my file. And I'm trying to get a value from this hash table and to store it into TNL. Well, here I have a check on TNL if something bad happens. So this is a hash table. So if I'm using a key that's not in the table, then I'm trying with the first entry of the table and moving that into TNL. But what happens if I do not have any key at all in my hash table, for instance? So in that case, I would have an empty value into TNL, and later I would try to access some memory at that empty value pointed by TNL. So what I have to do here is to make my program really sure that whatever happens, if TNL is not, if it's empty, we don't use the rest of the processing of the program, and in particular, we don't use TNL. Don't try to read that. So in that case, for example, we should just drop the packet and return from the function. And just with that change, just with this verification, I can compile again my program and I can now attach it. So I spoke about this error before. This is because it seems to have already a program running on the interface, so I can override it with the -false option. And now it works, and that's good. So I'm going back to the presentation. So that was an example of verifying a program for BPF programs running on the host. For programs being offloaded to the hardware, this is exactly the same thing. The only difference is that we can have additional errors, maybe because the driver of the NFP hardware is doing additional verification steps. So this is a good example here. We could have this kind of errors about an instruction which tries to call a BPF helper that would be typically the helper that we saw just before for reading a value from hash map. And if this is a helper not supported by the hardware, maybe because that's a helper dedicated to BPF tracing program and we don't want that on the NFP, or just maybe because it's not supported at all at the moment, then the verifier complains about this function not being supported, although this is not really the kernel verifier here, but the verifying part coming from the NFP driver. But it reuses the same buffer for output, so it's also an error message that we get in the console, so that's pretty convenient to debug. So now let's say we have passed most of the verifier. We are trying to JIT compile our program. Do we have any additional error messages that would happen at JIT compiling time? Actually, for programs running on the host, we don't really have specific messages related to JIT compiling because the JIT in Linux is so tightly linked with the verifier that every message that would be likely to occur at this step would already have been detected and dumped by the verifier and the program rejected. So there's no real difference when you try to load your program on this side. If you are trying to load it to the card, since the JIT compiler is in the driver and not in the kernel itself, so you have a small difference. Maybe you could have a bunch of messages that only occur at compiling time, and then that cannot use the verifier buffer for being printed to the console. So they would be, for example, in kernel logs that you could print with the message command. And here is an example of such a message. So if the stack is too large at the moment, that's some information you would get from the kernel logs, although we are trying to move as much as we can earlier in the process. And this message, for example, in a few weeks should be, in the development version of Linux, should be dumped into the console as well. So we're trying to make that as smooth as possible. And it's only a couple of messages really, and most of them you should not see. Most of the programs, once verified, should be offloaded smoothly. So now we have managed to load our program. That's good. We have passed the verifier. The program is stored somewhere in the kernel, possibly JIT compiled. And we have also created all maps required by the programs. We didn't see that in the example, but that would be done by IP or IP link or TC most of the time. So let's try to see what we have now on the kernel. the system, sorry, and see if we can dump some information. So for that, I'm using bpftool, which is a tool dedicated to introspection of BPF objects. So I'm going to install it on my machine. I'm going to the Linux sources. This is a BPF Next branch, but it's also available from the stable branch for a couple of months. I'm going into tools, bpftool, and what I'm doing is make install, and I want the documentation as well. So I'm adding doc install, and everything compiles and installs. And we are done. So I can just type bpftool. I get some information about the usage if I'm using bpftool prod. I have the list of the BPF programs running on my system, so that's good. I see here that I have an XDP program that I just loaded, which has the ID 7. So I can probably get more information about that program. If I type bpftool prog dump generated ID 7, that should not work, I think. That's because JIT compiling is not currently enabled on my system. Sorry, so I wouldn't have the translated instructions. So that's BPF bytecode not compiled into x86 assembly. Instead, just eBPF bytecode as we loaded it into the kernel, and which received a very few minute translations from the kernel verifier. So that's my program from the layer 4 load balancer, obviously. I also have some maps, I think. So there is one map which I can dump also. That would be ID 16. That's the value I got here. And currently the map is empty. It so happens that I have a script into this repository coming with layer 4 load balancer. There's a script which can be used to fill maps used for the demonstration. So here I'm using that script, telling it to retrieve the map attached to the program used on an FPP1 interface, to feed it with whatever data is in that CSV file. So let's have a look at the file very quickly to see what's in there. I'm not in the correct repository. Here I am. So this is a list of IP addresses that is used to tell the program, the demonstration program, to which host should be redirected, should be balanced the incoming IPs. I think there is a batch file which was created for from that CSV file and for filling the maps, which is this one. That's not really readable, but that's a bunch of commands: EPFTool, map update, ID, 1 key, and so on. And probably I have to make that file again if I wanted to fill the correct maps. Maybe not. So it was probably generated again anyway. Yeah. So my script is supposed to have filled the maps. Let's have a look now at the map. EPFTool map dump ID 16. The ID of the map hasn't changed. This is still the same map, obviously. And now I have plenty of values here. So this is a hash map. So each time I have a key and a corresponding value. So that's pretty useful actually. We can see a lot of things happening in the maps, and we can also edit the maps with bpftool, which is what was done by the script in the first place to fill the maps. And so from those maps, the BPF program of the demonstration example would be able to retrieve the host to which it should forward the packets, depending on the source IP address. But I'm not running the complete demonstration here. So this is just a small example of what can be achieved with bpftool. We can list maps and programs, we can dump them, we can load the program, pin it in the BPF virtual file system. We can dump the instructions and so on and so forth. So that would be, for example, a very simple programs, just doing R0 equals 0 and then exiting. That's exactly what we saw. That will be the same program, but compiled into x86 instructions, which I can probably do because it's not long to set. So if I'm first removing my program xdp off, I just detached and removed the program from my interface. Now I want to set JIT compiling on my system with that command, and that's done. And if I add my program again, I should be dump it with bpftool prog dump gt id7. Just the thing that changed is that it's a new program, so it's not the same ID, it's ID8. And here is the Intel list of instructions from the byte program. I could also, instead of JIT compiling it for the host, I could even send that program to the hardware because I happen to have Netronome cards on this machine. So what I will do now is I just remove the program again. I'm gonna offload the program to the hardware. So instead of using XDP here on the command line, I'm using XDP offload. And hopefully I should have offloaded my program. So I still have a program that's number 9 now. And I can nearly jump the instruction, except that my version of bpftool here does not support does not support instruction for the NFP hardware. We do have a version that supports it because we have upstream support for the NFP instructions into the library that's used by bpftool. This is in binutils dev package. So if you are using the latest version to compile bpftool with, you can get the instructions that they were compiled on the Linux by the Linux driver, but for the NFP hardware. So that's the list of all the instructions that are pushed to my NIC. So I'm going back to the presentation now. We have seen how bpftool can be used for dumping the instructions. So also for offloaded programs, we have some support incoming for with the latest version of binutils dev. So soon it should be in the version of bpftool that would come under distributions. And so last step would be attaching the programs now that we have compiled them, injected them into the kernel, JIT compile. Actually, we didn't see that step really because TC and IP-Link did it at the same time that they loaded the programs into the kernel. So even if for the kernel that's a different step, we didn't really see the difference. But once the program is loaded, it can be in the kernel without being attached to any hook yet, so without processing any program or anything. Just what you can get at this time is netlink exstack messages sent by the system to tell you that something's wrong when trying to attach the program. Typically, that would be the message we saw before. When there is already a program running on an interface, Netlink would complain. and say, no, that's not possible unless you tell me to override that program. This is exactly the same thing for offloaded programs, because we do have access to netlink messages also in the driver when trying to offload the programs. So you would get the same kind of messages here, and you don't have any difference. And once you have successfully compiled, verified, and attached your program, you can now run it on your system, and that's good. You can process packets. Except that sometimes your program just does not behave as you thought it would, so you try to debug that, you try to understand what happens in your program. And at this time, there is no debugger ready for BPF programs, so it's complicated to get some output from the program. So one thing that exists is a BPF helper, so again, a function that you can call from your program, and which is called bpftrace which is a bit like a printk or a printf. That would be for user space programs. Printk is for programs in the, for code in the kernel, and you can use that to dump some output from your program. Sorry, so let's just have a short example again about that. I'm changing the directory now, and in that directory I have a trace printk simple program, and so basically what it does is checking the length of my packet, and if that check that we saw earlier does not, as if my packet is not long enough for me to access to some data to return. And before I return, say imagine I have something more complicated, and I want to, at some point, I want to see what are the first 4 bytes of my packet. I want to see from a developer point of view, so I want to get some information about that, because it seems to be there seems to be an error. I thought that the first 4 bytes were the Ethernet type, but it doesn't happen to be. So what's wrong? Well, of course, it's not Ethernet type, it's a MAC address. So let's use this trace printk helper here. I'm gonna compile this program and just make a shortcut to the command line to compile my program. I have my trace printk.o here, and I'm gonna attach that. Before that, maybe I will remove some program in the interface. And now I attach my trace printk program section. There's no section name in that C source file, so this is the default section which is used, .text, and it works. And so now that I have attached my program, let's use another machine here, which is connected to the first one to, well, just to ping the first one. Okay, pings, everything works. And now I can have a look at the file in which this bpftrace printk prints some output. So there is a trace file under syskernel debug tracing, and tells me what's being written to that file. And if I use a pipe version, it's a pipe, so I get the output in real time. So if I stop pinging the system, well, I don't get any more output. And if I start again sending packets, well, I see each time exactly what I wrote in my program, the first 4 bytes of packet, and then the dump of those bytes. That's pretty convenient. That's something everyone working with BPF should know about. It's really, really useful to see what happens, except that it's not so performant, and except that it doesn't work with offloaded programs. So for offloaded programs, instead, we have another feature, BPF feature, which is supported, which is quite similar, except that it's more performant, but also a bit more complicated to use. That's why if you work on the host and just for debugging, you might want to use trace printk. but we have something similar, which is perf event output, working with perf event in the kernel to debug. In that case, it would debug some data from the packet directly. So I'm not going to show an example of that because I'm probably a bit late already in the presentation. But if you're interested in that example, we have an XDP dump application, which is in our repository. That's the last one we added here. So if you want to check events, you can just use that one and have a look. Last thing about debugging at runtime. So we don't have really an eBPF debugger at this time, but if you were too much confused at what your program's doing, you might want to try some of the user space interpreters that exist. So there is one in C, which is uBPF, one in Rust, which is RBPF. They don't have all BPF features. The support is not as complete as in the kernel, but you might want to try them if really you need to debug step by step. That's in user space, so it might help. A word about the other tools regarding BPF programming. So you have obviously libraries for managing eBPF programs. There is eBPF, which is in the kernel tree, and the tools eBPF, which can be used to load programs, dump maps, dump programs, dump information, do a lot of things regarding BPF objects, so maps and programs management. This is the one used by bpftool in particular. You have also something pretty similar in the BCC tools. So those are two libraries existing. I would advise to use the first one. I think this is more complicated at this time. We have been contributing to adding or updating support for the BPF system call to tools such as strace. So now you have the possibility to strace programs and to filter on the BPF system call and to see what the values returned by your program. So you could do that on IPLink, for example, and see what values the BPF system call returns when running IPLink. That can be convenient to see what's the value return, what is the exact error code if the output is not enough to understand what's happening. Sorry. And we've also been adding support for BPF system call in Valgrind too. And so the upcoming version, I think 3.14 version of Valgrind was finalized just today, but it's not been announced yet. So it received support for BPF system call as well. So you could check for memory leaks some programs using the BPF system call now. That's about it for everything related to tools and debugging that I wanted to tell you today. So for the next step that we have in mind, because we are still involved in the tooling, in the debugging infrastructure, it's really important for us to make it convenient to work with BPF at every stage of the process. So we have in mind to improve the components that exist already. So we are trying to improve error messages. Some of them are not so clear. We are trying to improve the existing tools to add new support for new BPF features or new features to help managing BPF programs and maps. The documentation too can be improved. We are working on several aspects on that. We would like to improve packaging as well. bpftool is packaged on the latest Fedora, but not on Debian or Ubuntu. So that's something we intend to work on in the coming days and weeks. eBPF also is packaged on Fedora, but not on Ubuntu yet. We want to try to help the community with keeping the tools up to date, which means, for example, if you get some new subcommands for BPF, some new parameters for the BPF system call, tools such as strace or Valgrind must be updated to reflect that support. So that's also some maintenance here that needs to be done from time to time. And possibly we would like to create new tools in the future. So maybe if we could find a way to implement an eBPF debugger, that would be really good. Also, maybe we could have a look at libpcap that is used by tspdump for converting expressions such as IP.dest or something like this to filter packets. So these expressions are converted into BPF instructions by libpcap, but that would be the old BPF syntax, which was before eBPF. So that's not really compatible with latest BPF features and developments. So maybe there will be an update needed on that side. So yeah, these kind of things we intend to tackle in the future. The good thing is that we are not alone, because the BPF community is increasing in size, in activity too. There is more and more activity about BPF, around BPF, for tracing, monitoring, but also for network processing. There are things like AFXDP or such features that are arriving and that will be used more and more in different aspects of networking. So that's really interesting. And so my conclusion for today is that even BPF programs do not run in user space, so are not trivial to debug and not easy to access and to understand what happens in the kernel when you get packets, for example. Well, even though it's not easy, you have a set of tools which is getting more and more complete and better. It's getting easier to debug programs really. In comparison with 2 or 3 years ago, it's really more simple today, and it's going to be even easier in a few months or years still. So that's a good thing. We have seen that we can dump the instructions at all the different stages of the process. So just after compiling it to an object file, and once we have loaded the program on the system, whereas the program has been JIT compiled or not, it's possible to get some output at runtime from the program with bpftrace, printk, or perf events. Perf events are also working on the host, obviously, but that's the only of the two methods working for offloaded programs. And one point that I just wanted to highlight is that really debugging offloaded programs is nearly as easy as for programs on the host. There are really little, not little, really few differences between running programs on the host and on hardware, except you get much better performance, obviously. So just to finish, here's a list of additional resources where you can find more information about BPF in general. So we have a getting started guide on our website that explains a lot about loading your first BPF programs. There's a section about offloading, of course, your programs, but you can find also some hints for programs running on the host. There is a partial list of information about some of the error messages that the verifier can give you if your program is rejected. So there is a kind of FAQ about different errors from the verifier in the kernel documentation. You might want to have a look at this if you get some errors you don't manage to understand. We have a lot of resources about eBPF in general on our website, including also some links to the sample applications, so the layer 4 load balancer or xdpdump or other ones we have about to come very soon. So feel free to have a look at those and to use them as a base for your own applications if you need them. Obviously, if you don't get any better hint for solving a problem, you can still have a look at the kernel source code for trying to understand what the verifier does, but that's quite complex. So I hope you can find an easier solution to troubleshoot your program. And I just wanted to highlight that there is some documentation from the kernel helper functions that can be called from the BPF programs. It was generated and installed when I ran doc install earlier. So if I'm doing the BPF helpers, here I have a list of all functions that can be called from a BPF program. So trace printk, for example, would be here. Lookup LM for doing a lookup from a map is described as well. You have, I think, as of today, there is like 88 such functions or so, not all of them being supported for networking programs. But just so that you know, there is this page existing, and there are versions on the internet that you can consult without having to compile the documentation. And that's it. Thank you. I hope you enjoyed the webinar. Thank you very much. I think this is time for questions.
Thanks, Quentin. So I put a question in the chat, if you can look at that, but I'll just give you the first part of it. It says, can you talk a little bit more on debugging eBPF programs at user space? And then it says, for example, do you know any plan on eBPF for user space debugging support or any other similar projects putting efforts on this area?
Thank you, Jennifer. So I think I answered in part to that question at the end of the presentation. I'm not really aware of any project regarding debugging BPF in user space, but this is something we've been thinking about for some time now, and I would like to have a look at it. Some of my colleagues too would like to explore possibilities in that direction. So I've heard the name of LGDB, which is a debugger coming with LLVM, I think, and I would like to see if anything's possible to somehow load BPF programs into that debugger and see if we can run a program step by step or something like this. But so that's, at this time, that's just ideas, and I'm not aware of any work being done on that topic right now.
Great. Well, Quentin, those are all the questions we have, and it's about time to wrap up. Will you give me a number between 1 and 78 for our winner of our Amazon gift card?
I don't know. I have 27 slides. Let's use 27.
27 is Chris Summers from Keysight. So Chris, I'll be sending you an email to follow up about winning the Amazon gift card. Thank you, Quentin, and thanks everybody for participating. Have a good day.
Thank you very much for attending the webinar. Thank you, Jennifer, again. Have a good day, everyone. Goodbye.